I'm Vivian Shwaikani. I'll be explaining you the part 3 of chapter 4, chemical equilibrium. As usual, let's start first of all by the objectives. In this chapter, or in this part, we have to do a quantitative study for a reversible reaction system using an ICE table. And second, we have to determine the quantity of a reactant or a product at equilibrium. Let's start by a recall of our previous parts. We said that an equilibrium is homogeneous when all constituents of the reactional system, it means reactants and the product, are in the same phase. However, an equilibrium is heterogeneous when the constituents of the reactional system are in different phases. And we studied something about the equilibrium constant that is denoted by Kc, and we said that for any chemical reaction represented here in general, Kc is equal to the multiplication of the concentration of the product, exponent their stoichiometric coefficient, over the multiplication of the concentration of the reactants, exponent their stoichiometric coefficient. We said also that the concentration of solids, liquid, and aqueous species doesn't figure in the expression of Kc, definitely in case of heterogeneous equilibrium. Those concentrations are considered to have a value that is equal to 1, and we said also that Kc depends on temperature, so its value changes when the temperature changes. Also, we have to consider that Kc is unitless. Now, let's start with our first objective, which is about the quantitative study of the system at equilibrium. To do this quantitative study, or to know how to make it, let's consider the following application. Consider the following reversible reaction. Br2 gas would give us in a reversible way 2Br gas. The given is at 1280 degrees Celsius, the equilibrium constant Kc for this reaction is found to have this value. The question is to calculate the concentrations of these species at equilibrium, starting from the following initial concentrations, Br2 initial having this concentration, and Br0 initial has a concentration that is equal 0 mole minus 1. Now, since we are dealing with a reversible reaction, we have to use what do we call the ICE table. What is the ICE table? E here, or I for the initial, C for change, as you can see here, and E for equilibrium table. Why? Because for the quantity, for example, of Br2, which is a reactant, we have actually three values. The initial one that is given here, the reacted quantity during the reaction that we have to determine, and the chemical and the quantity remained at equilibrium. Same for Br, which is a product. We have also three values for it. The initial one, the formed or the produced quantity during the reaction, and the total quantity at equilibrium. If you didn't understand well what do we mean by this, let's continue the application and you will understand. This is our reaction. This is a table. What about the initial quantities? The initial quantities are given in the application. So this is numerical values that are given. Now, what is the change? It means how much Br2 reacted and how much Br reacted also. Here, since we don't know the value of the quantity that has changed, it will be expressed by X. So, we will write here X for the quantity changed for Br2. And since Br2 is a reactant, the reacting or the quantity of the reactant decreases with time. So this is why we give here a negative sign, exactly as you saw in kinetic lesson. Then, for Br also, the quantity of Br produced depends on the quantity of Br2 produced, but it's double. Why? Because the stoichiometric coefficient of Br is 2. And since Br is a product, it means it is formed. We attributed here the positive sign, as you can see, because the quantity of the product is increases. So this is the initial state, and this is the change for each species. So at equilibrium, what would be the quantity of Br2? It is the initial minus the change, and that of Br, it is the initial, that is 0 in this case, plus that change. Now, So this is an ICE table, and here there is a remark that usually we use it for concentrations, but sometimes we can use it for number of moles or for anything else. This is the same table that is copied again here. You know that in this exercise we gave us the value of Kc, and Kc by definition equals the concentration of the product, that is here Br, exponent its stoichiometric coefficient, which is 2, divided by the concentration of the reactant Br2, and the stoichiometric coefficient here is 1. So what is the quantity of Br at equilibrium? It is simply 2x. So we replace Br here by 2x exponent 2, and the concentration of Br2 is also taken from the table. Kc here, the numerical value is given at the beginning. So we will get here a quadratic equation for x. So you can solve it usually as usual using maybe a calculator. Actually, upon solving x, you will find two values, this one and this one. Pay attention. In this case, x cannot be negative. So this value is to be rejected and this is to be accepted. Why it can be negative? Because after all, the quantity of Br is increasing. So x is positive here. Okay, now knowing this x, we can determine the quantity of Br at equilibrium, that is equal to 2x. Simply we multiply 2 by the value of x given, and we will get the quantity of Br at equilibrium. And we do the same for Br2 by applying also, by replacing x here by its value. This is how to do a quantitative study of a system at equilibrium. Now about this application, I will not ask you to pause as usual. I will work this application with you. Look here, I have this reversible reaction, and pay attention that all constituents are gas. So so we are in case of homogeneous equilibrium. The given is at constant T, this reaction has an equilibrium constant 15, starting from 3 mole of each species in 1.5 liter flask. Calculate the concentration of each species at equilibrium. So first of all, let's calculate the initial concentration of each species. We know that the concentration of H2 here is equal to the number of mole of H2 over V total. It's equal to 0 over 1.5 liter, which is the volume of the flask where H2 and the other gases are found. That is equal to this. Here there is an important note that is only for gases. If many gases are found in the same container as the example of our application, the volume occupied by each of them is equal to that of the container. Why? Because you know that the particles of a gas are really very far one from the other. So, and you know that a gas occupies all the space that is available to it. So if H2 is put in a container having this volume, the particles of H2 will be spread in all this volume. The same for F2, the same for HF. So to calculate the concentration, the initial concentration of F2 in the same way, this is the number of mole of F2 that is given here by 3 mole divided by the total volume, because F2, the particles of F2, as we said, are spread will be in the whole points of the container, and the initial concentration of HF is the following. Now, let's put these values in a table in order to be able to calculate the concentration at equilibrium. Here is the reaction, the given, and here is the table. Simply here we arrange the given. Here is the initial values which were found in the previous slide. That change as we did previously. It's minus x because H2 is a reactant, minus x because F2 is a reactant, is plus 2x for this. So at equilibrium, the quantity or the concentration of H2 will be 2, the initial, minus x, the change. This one is also 2 minus x, and this one, the initial, that is 2 plus 2x. The same given is repeated, and this table is copied again. Kc is equal, by applying the same in the same way, Kc, that is equal to the concentration of the product divided by that of the reactant. And here are the quantities at equilibrium. So we will get 2 plus 2x squared over 2 minus x. These values are taken from this table. It's equal to 115. By solving x, we will find a value acceptable for x that is equal to this value, and then we will find the concentration of H2 at equilibrium, that is 2 minus x, which is like this. That of F2, it is 2 minus x, and that of HF, it's 2 plus 2x, it is the following. Here, for the application 2, this is the given. I will ask you to pause the video and to do it alone. Here is the solution. Okay? Now, this is what we have to do for this part. I will ask you again to pause the video and to read what you have on the agenda and to do your homework. Thank you for watching, and I'll see you in the next part. That would be the final one.